Hello, everybody. I'd like to welcome you to the Critical Materials Institute webinar series. And we know that you're going to enjoy this series, and we're thankful that you join us almost every month. Today, I would like to not only welcome you, but tell you a little bit about the series and how everything will flow today. Many of you have been on this webinar series for many, many times, so nothing too much new. CMI, we actually broadcast this. It's hosted by Colorado School of Mines, and we broadcast, of course, from all over, especially these days. We're always looking for additional topics, and we would love to hear from you if you have any ideas for this upcoming new year. Interesting note about this particular webinar, we have the presenter that was our very first presenter in our series that started in 2015. So we're delighted to have him back. And this is a public webinar, and it is going to be recorded, and it will be at the aimslab.gov/CMI site under the webinars menu. And of course, at the end, we're going to hold all the questions to the end, but when you have them, I really encourage you to go ahead and put them in, because it does take a little bit of time to queue them up. And that makes it very helpful for us to have some of them already queued when we start that question and answer series. I would like to introduce our presenter today. And again, the very first presenter we ever had in 2015, and he's back again to share with us progress in his research. So Dr. Patrick Zhang, he has a PhD in metallurgical engineering from the University of Nevada, Reno, and he has over 28 years of experience in phosphate research. 9 of those years have been working with CMI on research background in recovery of rare earths from phosphate processing. And he has been a task lead during that time. He has served since 1993 as a research director for the Florida Institute of Phosphate Research, and this is Florida Polytechnic University. And he really has led this effort, all of his efforts, into global prominence by conducting more than 21 projects, over 80 research contracts, and books, articles. He has really just been prolific in his research, and we're delighted to have him here today again. And we're going to look forward to your presentation, Patrick, if you want to take it away.
Thank you, Cynthia.
You're so welcome.
Good afternoon, everyone. I understand I'm in computation with the DOE webinar at this hour. I think DOE has a webinar on funding opportunities for rare earth related projects. But I can assure you, you are at the right place. Because if you understand rare earth and phosphate, you're going to get funding more than you ever dreamed of. You may even get rich by producing rare earths from phosphate. This research has been a real collaboration among many institutions and private companies, including Oak Ridge National Lab, Colorado School of Mines, even some University of Utah, and even some universities in China. And Mosaic has been very supportive of this research from the beginning. I just want to give you a brief description of phosphate mining and processing, and the different mining and processing streams generated during the process, which contain rare earth elements. Phosphate mining in Florida is all surface mining using dragline. The phosphate ore consists of roughly 1/3 each of clay, phosphate rock, and sand. So the beneficiation process involves washing the clay first, deslyming, followed by sizing. After sizing, the materials go through a flotation process to remove the silica or sand. In that process, it produces a flotation concentrate and also a pebble product, which does not need flotation. So the pebble product accounts for maybe 20 to 30% of the product. The flotation concentrate accounts for 70%. So this phosphate rock product is shipped to the acid plant where sulfuric acid is added to react with phosphate rock to produce a slurry of phosphoric acid and phosphogypsum. This slurry is filtered using a filter pan or other type of filters to separate the phosphogypsum from phosphoric acid. The phosphogypsum is pumped to a stack, gypsum stack, and the phosphoric acid is further evaporated to increase the P2O5 content. The filter acid generally contains about 30% P2O5. And by a two-stage evaporation process, the acid is concentrated to roughly 54% P2O5. So during this entire process, we generate waste clay, also called the slime or phosphate clay, which is pumped to a settling pond. The clay, as I pointed out, accounts for 1/3 of the phosphate ore. And also flotation tailings. Flotation is a fatty acid flotation, amine flotation, two-step flotation process. The flotation tailings is pumped to the mine cut for reclamation. So in the acid plant, you generate phosphogypsum, phosphoric acid, and also a phosphoric acid sludge, because during the evaporation process, as the P2O5 concentration increases, lots of the metals like iron, aluminum, rare earth elements precipitate out as a sludge. So this acid is treated currently by a centrifuge. The underflow of the centrifuge product called the phosphoric acid sludge is currently used to make low-grade fertilizer. So our research first was to understand the occurrence of rare earth elements in each of the process and streams. First, we investigated flotation tailings. This is mainly the amine flotation tailings. We found that the rare earth elements concentration does not have obvious correlation with the P2O5 content. That means there should be rare earth minerals instead of just calcium substitution in the phosphate crystals. So we use a mineral analyzer to determine some of the rare earth compounds. We did found monazite and xenotime. These are two types of rare earth minerals in this flotation tailings. By the size distribution, you can say the rare earth minerals concentrated in the middle site of the flotation tails. So SEM analysis did find some particles, like monazite particles, as you can see from this slide. There's obviously a clear separate monazite particles in the flotation tailings. This is a analysis of the monazite particles using EDS to actually determine the concentration of the monazite particle. As you can see, it contains various rare earth elements, including lanthanide, cerium, neodymium, thorium, and uranium. SEM image also shows particles xenotime with its yttrium phosphate mineral in this amine tailings. So we also determined chemical components of this yttrium phosphate compound. It contains various rare earth elements, particularly yttrium, is a major content of this mineral. So in conclusion, based on those research, we found that the majority of the rare earth elements in this flotation tailings exist as monazite and also a small amount as xenotime. In that regard, generally in the phosphate rock, we have monazite, xenotime, and calcium substitution in the phosphate crystals. This there are three forms of rare earth occurrence in phosphate ore in general. And also based on some leaching tests and chemical analysis, we quantify the rare earth elements occurrence in phosphate rock, roughly 20 to 30% as monazite, about 30% as xenotime, the remaining as calcium substitution in phosphate crystals. Phosphogypsum is another major product, waste or byproduct containing rare earth elements. So we also studied the occurrence of this rare earth elements in the phosphogypsum. Many research studies, including our research, indicated that in the acidulation process, in the chemical processing plant, the rare earth elements in the phosphate rock reports to much of the report, up to 70% report to phosphogypsum and 30% in the phosphoric acid. But most of the rare earth elements actually are initially dissolved. They are not undissolved rare earth compound, because when we run the leaching test on the phosphogypsum using dilute sulfuric acid, we could recover much of the rare earth elements, up to 80% from the phosphogypsum. That's the indication that those rare earth elements were initially actually dissolved. They just probably got reprecipitated or absorbed on the phosphogypsum surface. So it's easy to leach. If they exist in rare earth minerals, you could not leach with dilute sulfuric acid. So in the acidulation process, you get roughly 70% of the rare earth actually dissolved in the acid tank. But a large portion got precipitated onto the phosphogypsum. And also, the rare earth in the phosphoric acid eventually ends up in this phosphoric acid sludge if the evaporation is practiced. Some of the phosphoric acid plants have the evaporation process, some not. But if you have the two-stage evaporation, then most of the rare earth elements in the acid eventually reports to the sludge. As we will discuss, that's a stream with the highest concentration of rare earth elements. Why we think this is a significant? The rare earth elements in phosphate. First, the rare earth elements in Florida phosphate contains over 50 or close to 50% of yttrium and heavy rare earth elements. And these are the more critical rare earth elements. We ran this on almost every stream. So roughly it's 50%, some maybe like 49%, some 52%. But 50% is a good number in terms of yttrium, the heavy rare earth content in the Florida rare earth elements. In terms of volume, this is this shows analysis of rare earth elements in some sludge samples we collected over a 3 years period. As you can see, the total rare earth element in this sludge is close average 2,600 ppm. It's very high, and particularly some of the more critical rare earth elements. Just in Florida, we generate roughly 450,000 tons of this phosphoric acid sludge. So the recoverable rare earth elements based on this table is like 262 tons of yttrium, 172 tons of neodymium. So these numbers represent, as you can see, much of the U.S. demand for this element. For yttrium, it's like 56%. That's the highest. For other, we have 8%, 34%, 80%, 73%. So this one stream is very significant source of rare earth elements. When we look at phosphatic clay, the numbers are even more impressive because the annual production of this waste clay are roughly 20 million tons. So the recoverable elements, this on an annual basis is over 1,000 tons of yttrium. And this will satisfy, I think, in nearly the entire world demand for yttrium. So the other elements, for example, U.S. demand mostly is like 100%, 200%, or 400% for some of the critical elements. There's flotation tails, which is easy to process because as we point out, the rare earth elements in this tailings exist as the rare earth compounds, either the monazite or xenotide. So they are very heavy, so they could be separated using gravity separation. I will discuss that later. So based on this 3.9 million tons per year amine flotation tailings, again, we can produce a significant amount of critical rare earth elements, meeting a significant portion of the U.S. demand for this element. Phosphogypsum, again, annual production roughly 20 million tons, which also represent much of the U.S. demand for this rare earth element, particularly yttrium, neodymium, scandium. So as I point out, we understand the occurrence of rare earth elements in different processing streams. Based on those analysis, we came up with different strategies for recovering those elements from each of the processing streams. For this waste clay, we propose this overall process and flow sheet. We have not finished all this research yet, but we have gone through many of the steps. See, in this overall process and flow sheet, we propose to recover the rare earth elements, phosphorus, magnesium, and uranium. Because as I point out, the phosphate ore contains roughly 1/3 of the phosphate ore. So since the desliming practice started in Florida, we have accumulated over 2 billion tons of this slime, which contains over 600 million tons of phosphate rock and million tons of rare earth elements. So our strategy including a cyclone separation step to remove the clay particles, because that caused a problem for whether it's flotation process or physical separation process. So we remove the clay using small hydrocyclones. Then the underflow from the hydrocyclone goes through a flotation process to further concentrate phosphorus and rare earth elements into a concentrate. Then we use a stage-wise leaching process. First, there's low acid, like 3.5 pH, to remove the magnesium and recover it as a product, either as a pure magnesium or magnesium oxide product. After removing of the magnesium, the phosphate rock goes through a stage-wise leaching process so we can recover the rare earth elements and the phosphoric acid product. So this can, in this way, we call it comprehensive recovery of all the valuable elements from this waste product. So this just so we did some clay separation using hydrocyclones of different diameter, and then use a flotation process to concentrate the underflow product and then acid leaching to recover the rare earth elements. This is we did a implant testing using a pilot scale hydrocyclone. So we tested 4-inch, 2-inch, and 1-inch hydrocyclones. As many of you know, the smaller is the cyclone, finer is the cut size. We need to cut like around 5 microns or less. So small hydrocyclones are required for this type of work. So we did the leaching of the cyclone underflow directly, and also leaching of the flotation product. This is the leaching of the cyclone underflow product. We used the 75 degree Celsius stoichiometric ratio of sulfuric acid to calcium oxide 1.05, about 30% solid, leaching time 160 minutes. This way, we could recover about 55% of rare earth elements, over 99% of the phosphorus from this. The cyclone flow underflow product because we removed much of the clay particles, so we can use flotation process to further concentrate phosphorus and rare earth containing materials. This shows effect of acid collector dosage and also a depression dosage. As you can see, in most cases, we got the recovery. The red line represents recovery of rare earth. It's like over 80% by this flotation process. So by this flotation, we concentrate the rare earth concentration up to 455 ppm. The total recovery in the concentrate is about 80, almost 82%. As I point out, when we did the leaching directly on the cyclone underflow, the recovery was not very high, it's 55%. So in this case, we increase the temperature and also the concentration of sulfuric acid. In so doing, we increase the leaching recovery to over 80%. For the amine flotation tails, we have different strategy. First, because the rare earth in this stream exists at monazite and genotype. The specific gravity of monazite is about 5, genotype 4.6, and the phosphate about 3.2, and silica 2.6. So this makes it easier to separate the rare earth containing materials from other materials using gravity separation. In this case, we just use a shaken table. So we got the shaken table, we recover the rare earth containing minerals. We do a grinding flotation to further increase the rare earth concentration in the product for final recovery of the rare earth elements. Again, this is a pilot scale shaken table. As you can see, just by this one stage flotation, gravity separation, we concentrate nearly 40% of rare earth elements in only about 12.5% of the mass. So that's a very good separation. So the rare earth concentration is increased from about 200 ppm to 657 ppm in the concentrate. If we do flotation on the gravity separation concentrate, the rare earth concentration is further increased from 500 ppm to 1800 ppm. And the P2O5 content also reached 26%. And the P2O5 recovery is 82%, rare earth 73%. This is from the gravity separation concentrate. The leaching test, we used the standard leaching process for manufacturing of sulfuric acid, phosphoric acid. We achieved 61% leaching efficiency. From the flotation concentrate, the recovery is about close to 60%. For phosphogypsum and the phosphoric acid sludge, we use this current leaching process, and also using dilute sulfuric acid to recover the rare earth elements from both gypsum and the phosphoric acid sludge. For phosphogypsum, used under this leaching conditions, we got 82% recovery of rare earth elements. For sludge leaching, three-stage current leaching with the sulfuric acid, the recovery is 85%, and rare earth concentrations in leachate is about 290 ppm. Currently, under the CMI program, we focus on recovery of phosphorus and rare earth from phosphoric acid sludge. Although the rare earth concentration in this sludge is the highest among the phosphate mining process and streams, phosphorus still has much higher value in this sludge than rare earth. So in order to improve the economics, you have to recover the phosphorus as a high value product. Otherwise, it's still very challenging to recover the rare earth elements economically, even though the high concentration is much higher than other streams. So we are doing that. We're going to try to get this phosphorus separated from the sludge first, then get the rare earth elements leached and recovered. We just received a research grant from DOE phase 1 to come up with a research strategy to actually produce rare earth products from this sludge. If we are lucky, we get phase 2, we would be doing a pilot scale testing program. And also phosphogypsum purification and rare earth recovery, we continue work on that. Phosphogypsum is tricky because currently it's regulated by EPA because of a low level of radioactivity. So phosphogypsum has to be stacked. After it's pumped to the stack, you cannot touch it anymore. So in order to recover this element, rare earth elements under the current environmental regulation, we have to reduce the radioactivity level down to 10 picocures per gram. That's a radioactivity level. So we are doing that type of research, trying to first reduce the radioactivity, then recover the rare earth elements from phosphogypsum, because the sheer volume of the phosphogypsum make it a very viable source of rare earth, but we have to get the radioactivity reduced first. Of course, we continue working on this clay. Waste clay is the most challenging problem, probably because it contains roughly 50% clay minerals. And the particles are very fine, maybe 50% less than 1 micron. But the potential is huge in terms of both rare earth elements, phosphorus, and phosphorus. This research is supported by the Critical Materials Institute and Energy Innovation Hub, funded by the U.S. Department of Energy, Office of Energy Efficiency and Renewable Energy. Advanced Manufacturing Office. FIPR also provided funding for this project, both in terms of a matching fund for the CMI project, also some separate project funded by FIPR alone. We appreciate Mosaic's support for this project. Many people participated in the discussion, the evaluation of our research, and also in providing samples for our research. And thank you very much. I'll be glad to take any questions you may have.
Patrick, I'd like to thank you for a great presentation and kind of sharing with us the research that you're doing, and in particular the significance of phosphate as a rare earth element feedstock, and processes that you're going through in terms of leaching any of the rare earth elements. And again, research possibilities. And you promised you would do that at the beginning, that if people are on the line, you're going to share also even some, future ideas and opportunities which you have. I know there are going to be a lot of questions, and currently right now, I'm going to open up the floor for people to type in their questions. And it looks like we have one that is ready for you, and another one just came on as well. So Patrick, if you want to read the question and answer it for us.
Yeah, the first question is from John Carr. The question is, do you have an estimate on the approximate mass of phosphoric acid sludge per ton of phosphate concentrate entering the phosphoric acid plant? Yes, based on industry experience, the amount of sludge generated roughly 5 to 20%. So that's a large range, 5 to 20% of the P2O5 input. So could be 5% or 20%, depending on how your plant operates. So up to 20%, but at least 5% of the P2O5 input. The second question also from John Carr, is there a pilot plant operating recurring REE from the phosphoric acid evaporator sludge? I'm not aware of a pilot plant, at least probably not in the United States. Another question from ASF Redwen, I guess. What might be the reasons for low recovery from clay related to clay properties? If so, what critical properties of clay? I think there are several reasons for this low recovery. One is there's still some clay particles, even in the hydrocyclone underflow or our flotation concentrate, which clay particles interfere with any chemical processing. Another reason is probably because of some rare minerals, because like the monazite or genotime, if its temperature is not high enough, you don't get high recovery. So I think one is the clay particles in the system, another is the rare earth minerals, which are not readily leachable. This question from Amir, do you think ionic liquids can be promising approach for the recovery of REs with regard to the environmental impact of the chemical acid processing? I believe so. I think we we sponsored a small project many years ago on recovery of rare earth using ionic liquids. It was not a great success, but I think we still think it's a approach worth further studying.
We do have some time. There was the last comment was thanks. We do have some time for additional questions. And while we're waiting for any additional questions, what I wanted to do is to remind you that this all of the webinars are archived, and in about a week you'll be able to access this particular webinar. And of course, always being part of the CMI family, Patrick is always available for any additional questions. And Patrick, I guess while we're waiting for the potential of any additional questions, I wanted to ask if you thought there were any other, you'd like to expound on any other opportunities out there for research and or working with your organization.
I think bioprocessing is a very important field for rare earth recovery. We've been working with the Idaho National Lab and Livermore National Lab. We provide some samples. We still believe this technology has potential. Another field is some relatively inexpensive solvent. Because due to the low concentration in any of this phosphate processing streams, leachate, you're not going to generate leachate with very high rare earth concentration. So the traditional solvent extraction is very difficult to achieve economical results. So maybe inexpensive solvents or any type of solid that can absorb the rare earth from a low concentration leachate is worth studying.
Thank you. It looks like we've got 3 questions queued up.
This question from Zhang Li. What type of techno-economic research would you suggest for scale-up RE recovery from phosphate processing? CMI has a techno-economic team at Purdue University and also Oak Ridge National Lab. We have been working with them, trying to get an idea about the economics and technical feasibility. I think mainly it's economic feasibility is very important. So one question from John Carr again. Have you used hydrochloric acid instead of sulfuric acid in leaching the sludge? If so, what difference did you find? Yes, we have. The reason we focus on sulfuric acid in most of the research work is that we want to incorporate our process into the current phosphoric acid manufacturing process. If we use sulfuric acid, we have this can be the waste acid could be recycled to the gypsum step, so we don't generate new waste treatment requirements for the phosphoric acid plant. But yeah, hydrochloric acid leaching is more effective than sulfuric acid. And also we are going to try nitric acid leaching as well for phosphoric acid sludge.
Patrick, I'd like to thank you again for a great presentation. And while we're either waiting for an additional question and or timing is perfect for the end of this particular webinar, again, recording available at aimslab.gov/CMI under the webinars menu. Also, this was our last webinar for the year due to the holidays. Our next webinar is going to be on January 26th. Bridging Hydrometallurgy and Biochemistry, a protein-based process for recovery and separation of rare earth elements, and presented by Dan Park from Lawrence Livermore National Lab. Obviously, information will be available in the critical times, so please stay tuned. We want to wish everybody a great year end, an amazing holiday season, and we'll look forward to seeing you again in January.
Again, thank you.
Yeah, thank you so much. And as mentioned before, we're always looking forward to suggestions for webinars to serve our CMI community. So again, we'll see you in the new year and we'll look forward to your suggestions. We may have one more question. Nope, that was a thank you. All right, fantastic. Thank you, everybody.